So let's talk about scale modeling. We're going to use our non-dimensional parameters that we now know how to find in order to do scale modeling, and it's very important, very powerful. So what you have to do in order to do scale modeling is get what's called similarity. To achieve similarity, first thing you got to do is make the model look just like the prototype. The prototype is what you're trying to find information out about, so that might be the actual wing you're trying to design. The model is what you're going to test and get some information, try to apply that to the prototype. So the first thing you got to do is get the model and the prototype geometrically similar. And to get it geometrically similar, you just make it look alike, but one is small. So all the dimensions have to scale the same. The other thing you got to do is make all the angles and flow directions the same. So for instance, if you have a prototype wing, okay, and it has an angle of attack of alpha 1, then your 1/3 scale model, okay, looks the same but smaller. You don't scale that angle of attack. The angles stay the same, alpha 2. So alpha 1 equals alpha 2. Okay, so angles that stay the same, all the dimensions scale. Okay, so how do you do the scale modeling? Well, what you do is you equate all these non-dimensional parameters you have. So the first thing you got to do is figure out how to run your model test. And you're going to use all those right-hand side ones, all the ones with, you know, as you said, F of Reynolds number and so forth. All those things inside that parentheses with the F. That's what you need to do to figure out how to run your model test. So let's write that up here because it's very important. Use the right-hand side to figure out how to run model test. Okay, so for instance, if you have drag on a rough sphere, if you go through the process we did before, that Epson method, you're going to find a coefficient of drag is what we're going to call it, your left-hand side, and that's going to be d drag over 1/2 rho v squared times pi over 4 d squared. Okay, you wouldn't actually come up with this 1/2 and this pi over 4, but you can always add in constants if you want. And here, if you add in the pi over 4, you get an area, and if you add in the 1/2, you get a kinetic energy kind of term. So that's why those constants are thrown in there. But our CD, this is your left-hand side, okay, is going to equal some function of rho v d over mu and epsilon over d. This is a rough sphere. You saw this in the lab. This is your Reynolds number. This is a roughness scale. Okay, so in order to achieve this similarity we're talking about, what we need to do is make sure that those right-hand side variables are the same for your model as they are for your prototype. Wherever it is that you want to get information about your prototype, you're going to calculate the Reynolds number and use that in your model. Okay, so in other words, your CD for your model is some function of, and it's the same function model of prototype, of Reynolds number and epsilon, call it Reynolds number model, epsilon over d model. Okay, and you can say the same thing then for your prototype. CD prototype equals F of Reynolds number prototype epsilon over d prototype. So what you want to do for your model test, figure out how to run your model test, make RED model equal to your Reynolds number prototype, and the same for your roughness factor. So you want to make Reynolds number for your model equal to Reynolds number for your prototype, and the roughness also. E over D for model equals epsilon over D for prototype, not E, epsilon. That wasn't a lie, just something I said wrong. Okay, then the right-hand side is the same. So once you get this, once you get if this, then the left-hand side is the same, or the CDs are the same. So you use the left-hand side, those CDs, to find your prototype answers. That's what you're looking for, prototype answers. Okay, so if everything on the right-hand side is the same, well then the left-hand side has to be the same as well. So that means CD for your model is going to equal CD for your prototype. And that drag that you're trying to find, well that's embedded in your CD. So you're going to be able to solve for your drag. That's what you're trying to find. So you're going to use your CDM that you can calculate from the test that you do on the model, drag M. So you're going to get drag M, you're going to know all the geometry and all that and the fluids calculated from DM to say that, okay, CDM, you're going to calculate that and then you set it equal to your CDP, which is drag over 1/2 rho V squared pi over 4 D squared for your prototype. And then solve for drag of your prototype. Okay, and that's what you're trying to find, prototype drag. So that's how you use the model test. Okay, so first you set up your test so that you equate all your non-dimensional parameters on the right-hand side. Once you do that, you run the tests, and you're going to get a D sub M if you do that. A drag, you're going to measure drag on your model. If you have that measured drag, well, you can calculate CDM. If you have CDM, that means you know CDP. Okay, and from the CDP, you can calculate that prototype drag. So that's how that works. Let's do a couple examples. Okay, so let's say we want to test a wing again, and we know it's going to fly at 50 meters per second. Angle of attack is 10 degrees, and our chord length for the prototype is 3 meters. And it's going to fly at 5,000 meters of altitude. And by the way, there's a table in the back of your book that has to do with altitude. It'll give you properties at altitude, at least density. So what you want to do is find the expected lift on that prototype by testing a 1/6 scale model in air at sea level. Okay, so what we're going to find is angle of attack, velocity for the model, and then what our expected lift will be on this prototype. Okay, so what we got to do is use our non-dimensional solution from before. And what we had was that L over rho V squared C squared. And we could have thrown in a 1/2 there if we wanted, or pi over 4, but this is directly what we got when we did our example. Equals rho VC over mu alpha, or F of Reynolds number based on the chord length and alpha. Okay, so let's do part A. For part A, find the angle of attack for the model test. Well, if you remember, for similarity, what we need is all the angles to be the same. So for geometric similarity, alpha model has to equal alpha prototype, which is 10 degrees. So that's easy. Nothing to it. Okay, B for, what this is for dynamic similarity. Oh, sorry, nope, that's for kinematic similarity. Then the right-hand side values have to be the same. Okay, so for the right-hand side values the same, well, we already got alpha the same. So what we need is this Reynolds number to be the same. So we need our rho for our prototype times V for our prototype times C for our prototype over mu for our prototype equal to rho model, V model, C model over mu model. Okay, and we also happen to know it's a 1/6 scale model, so C model has to equal 1/6 C prototype. All right, so let's just rearrange that. We get Vm. We're trying to find the velocity for the model test in part B. So Vm is rho of the prototype over rho of the model. Cp over Cm, which is going to equal 6. mu m over mu p times velocity of the prototype, okay, which is a given. So what we need is our rhos and our mu's, okay? So from table A6, we find rho for our prototype at 5,000 meters is 0.7361 kilograms per meter cubed at z equals 5,000 meters. Okay. And we also find our T at 5,000 meters, our temperature, is about 255.66 K. I don't know why they give us 0.66, but all right. So we got our rho. We also need our mu for our air up there. It's going to be a little less viscous up there at 5,000 meters. So below table A2, you're going to find some equations that will relate air viscosity to temperature. And I'm going to use the one mu prototype, that's what we're trying to find right now, over mu naught, that's given, is about equal to T over T naught at 0.7, and we're given a T naught under that table of 273 K and a mu naught 1.71 times 10 to the minus fifth kilograms per meter second. Okay, take that, plug it in, find all your values, and I'm not going to go through all the math, but what you get is Vm equals 203.2 meters per second. So since it was smaller, you end up with a bigger velocity, which is about 450 miles per hour. Okay, so what we want to do is run, if we want to simulate 50 meters per second on our prototype wing, we want to run our model at 450 miles per hour, 203 meters per second. So this simulates 50 meters per second on a large wing. And that way we have kinematic similarity. Okay, so the last thing then is dynamic similarity, which basically says if we get that kinematic similarity, the right-hand side, then our left-hand sides are also equal. So we can say LP, our left on our prototype, over rho of our prototype, V of our prototype squared, C prototype squared, equals the same thing for the model. LM over rho M, VM squared, CM squared. Okay, and now we can just rearrange this. Lift on our prototype, that's what we're trying to find, equals rho prototype over rho model, V prototype squared over V model squared, C prototype squared over C model squared, times LM. What I get when I plug that in, 1.34 LM. Okay, so basically you do your model test, 450 miles per hour, you get some lifts, and then you multiply that lift by 1.34 to get your prototype. All right, a couple more examples. Here's just an example of what you usually do is you don't just do one point like that previous example. You do a whole range of points. So a whole range, in this case, this is pipe flow. It's called the Moody chart, and they did a whole range of roughness and a whole range of Reynolds numbers, and then they got a function for each of those, and they can then you can just look up if you calculate the Reynolds number and the roughness, then you can find a friction factor, and that's going to help you find that HF that's in the energy equation, the frictional head losses. Okay, so the values, notice all the values in this chart are non-dimensional. Okay, that means you can only use it on 1-inch pipes. Okay, different example. Testing drag on a 1/10 scale model car in a wind tunnel. Okay, first of all, what velocity range do you need in the wind tunnel to achieve similarity for a car going 10 miles per hour to 80 miles per hour? Okay, so we want a range. So we need the model velocity that corresponds to 10, and the model velocity corresponds to 80 miles per hour. So again, if you're trying to find model information, how to run your model, you want to use the right-hand side parameters. So assuming that we're going to end up with something like we did with the sphere, CD is a function of Reynolds number with some scale, and I'm not sure what we would use for a car. Some length scale. And epsilon over d, it could have roughness as well. We'll just say it's like a sphere. Okay. It's not a sphere though, so it's going to have a different function, and that's what you would have to test. Each car would have a different function for CD. Okay, so what we need to do is get these Reynolds number and epsilon over d the same in our model. So if we're trying to find the velocity, that's contained in our Reynolds number. So we need to equate Reynolds numbers, and I'll call it Reynolds number sub b, where b is some length scale of your car. So a big car would have a big B, in other words. Could be the width of the car or something like that. B equals a length scale of some sort. Okay. So since we got to say the Reynolds number for the model is equal to the Reynolds number for the prototype, you're going to say, okay, rho model, V model, B model over mu model equals rho prototype, V prototype, B prototype over mu prototype. So VM equals VP, BP over BM, because these are going to be run in the same fluid, so they're going to cancel out. Okay, so the V of the model is just going to be, well, BP over BM, if this is a 1/10 scale model, well, that's going to be 10. So that's 10 VP. And I didn't leave enough room here, but that means it's 100 miles per hour to 800 miles per hour. Okay, so that's the range you're going to have to run your model test at, okay, on your little die-cast car. We could also test this in the water tunnel. Let's see what range of velocities we would need if we use the water tunnel instead. Okay, in that case, you're not going to be able to cancel out your mu's or your rho's. So what you need to do is figure out what those are. Mu prototype is going to be mu for air, 1.8 times 10 to the minus fifth kilograms per meter second. And the model is going to be water. And the same thing for the rho's. Rho prototype is air, rho model is water, so I'm not going to go through all those, but there's a big difference. Plug it all in, and you're going to get VM equals 6.7 VP. All right, so we need 67 to 536 miles per hour. Okay, very fast for a water tunnel for sure. So then, how do you approximate the drag using that information? Well, what you do is you run it at these ranges of velocities. You collect the drag on the model. So for each REB, you measure drag, measure a model drag. Then CDP equals CDM. So you use that model drag to calculate CDM, calculated from DM, and then you can use that to calculate DP, which is what you're trying to find. All right, so that's it. Only one video for this time. It was rather long, but you can go ahead and take the quiz now.